Welcome to the last part of the lecture. We're going to talk about displacement formulation solution strategy. Here's an example. It says, find a stress, a strain, and displacement distribution for a hollow sphere under uniform internal and external pressure. Note that the inner radius is A, outer radius is B. We have uniform pressure Pi inside and uniform pressure Po outside. The sphere is subject to constant external and internal pressure, and there are no body forces. B is equal to 0. So solution is spherically symmetric. When the solution is spherically symmetric, there is no variation along theta and phi in spherical coordinates. So partial theta is equal to partial phi equal to 0. We're going to see more about the spherical coordinate in the next few slides. But before that, these are some biomedical motivations. We can simplify the model for a stress in saccular aneurysm with a uniform sphere with constant internal and external pressure. The aneurysm may occur at different locations in the body, in the legs, near heart, in the brain, and you see in most of the cases they are not completely spherical, but a spherical model can predict the deformation behavior pretty well. These are a few CT scan images and biological samples with saccular aneurysm. Given the geometry of the problem, which is spherical, and the spherically symmetric loading that we have, the solution is most convenient to be expressed in spherical coordinates with respect to r, radius, theta, and phi, the angles. Here are some hints. The spherical coordinates, we have polar angle phi and theta, the angle with a spin axis. We can express x, y, and z with respect to r, theta, and phi. And also we can express dv, the volume, in terms of, again, r, theta, and phi. The Navier equations in spherical coordinates takes this complex form. Note that we have I, omega r, and omega phi that needed to be substituted in these equations. We don't care about how we derived these set of equations from Cartesian equations here, but as a hint, it's simply using the transformation from Cartesian to spherical coordinates. Implemented on the Cartesian form of our Navier equation. Also, the kinematic equation in spherical coordinates takes this form. So for epsilon rr, epsilon theta theta, epsilon phi phi, and epsilon r theta, theta phi, and r phi, we can find a relation with respect to ur, theta, and phi. And the constitutive law in a spherical coordinate is simply the same as the constitutive law in Cartesian coordinates, but just replacing I and j instead of with x, y, z, or 1, 2, 3, this time with r, theta, and phi. For an isotropic medium, the stiffness tensor has no preferred direction. An applied force will give the same displacement relative to the direction of the force, no matter the direction in which the force is applied. That's basically the case in spherical coordinates too. Okay, let's approach the solution of our pressurized hollow sphere. The first step is drawing the force diagram of the problem that we have here. The second step is simplifying the equation for the displacement formulation. But pay attention that we know our case is a spherical symmetry. So all of the partial derivatives with respect to theta and phi are equal to 0. Basically, all of these terms will be 0 and cancels out. So the deformation formulation reduces to this small relation, lambda plus 2 mu, differentiation with respect to r of 1 over r square, multiplied by differentiation with respect to r of r square ur plus pr. We have to integrate it to find ur as a function of external loads or pressures. Know that pr is not a function of r, theta, or phi, so it's basically it disappears. And integrating twice with respect to r, we get ur is equal to ar plus b divided by r square. A and b are constants that we're going to find based on the boundary conditions later. The fourth step is using kinematic equation to calculate strains based on displacement. We've already calculated the displacement, and we know the spherical coordinate representation of kinematic equations. Again, we benefit from a spherical symmetry to get rid of all of partial derivatives with respect to theta and phi. So all of these terms cancel out. As a result, the solution is reduced to epsilon rr equal to partial ur partial r, which becomes a minus 2b divided by r to the power of 3. For e theta theta and e phi phi, we have ur divided by r, which becomes a plus b divided by r to the power of 3. And for off-diagonal elements, we get only 0. And the fifth step is using constitutive law to calculate stresses. We already know that the constitutive law in a spherical coordinate is similar to the one in Cartesian coordinate. Here it is Hooke's law, but just substituting I and j with r, theta, and phi. We've already calculated a strain tensor, so let's work out the elements of a stress tensor. For sigma rr, we have E divided by 1 plus nu epsilon rr, which is a minus 2b divided by r to the power of 3, plus nu divided by 1 plus 1 minus 2 nu delta rr, which becomes 1, epsilon kk, which is the trace of strain tensor. It's epsilon rr plus epsilon theta theta plus epsilon phi phi. Okay, this was epsilon RR. This is 1. And the trace of the strain tensor epsilon kk is basically 3a. Note that minus 2b divided by r to the power of 3 cancels the other 2 plus b divided by r to the power of 3. So basically this becomes 3a. That's for sigma RR. For sigma theta theta, we get E divided by 1 plus nu epsilon theta theta, which is A plus B divided by r to the power of 3 plus nu divided by 1 minus 2 nu delta theta theta multiplied by the trace epsilon kk. Again, you know that this is epsilon theta theta. Delta theta theta is 1. Oops, delta theta theta is 1. Delta r is 1 as well. And epsilon kk is 3a. The same we have for sigma phi phi. For the off-diagonal elements, sigma r theta, sigma r phi, and sigma phi theta, we get all to become 0. The reason is epsilon r theta, r phi, and theta phi are 0, and delta r theta, r phi, and theta phi are 0 as well. So the off-diagonal stress elements become 0 as well. Okay, now we have to calculate the integration constants A and B by enforcing the stress boundary conditions. We use the traction stress relation at the boundary surfaces to find the boundary values for stresses, and then use that to find the constants A and B. At the inner boundary, so inner surface, R is equal to A. The forces along the pressure is along the radius of the sphere, so it's along R. So the traction at A is basically equal to Pi 0, 0, a pressure along the radius. Writing the relation between traction and stress, we get TA1 is equal to or basically TAR is equal to sigma RR NR plus sigma theta R N theta plus sigma phi R N phi. For the normal vector to the inner surface, it is along the radius but in the opposite direction. So that's basically n of A. Note that this is again along the radius and along in the same direction for the normal vector of outer surface. So n at A is 1 is -1, 0, 0. Using both those two, we know that n theta is 0 and n phi is 0 as well. And we have sigma rr. So basically sigma rr becomes equal to pi. For the outer surface, r is equal to b. The traction vector at B is equal to, again the pressure is along the radius, but in the opposite direction. It's toward the center of a sphere. So we have minus PO 0, 0. The normal vector there, the normal to the surface there, as I said, it's along the radius again and in the same direction. So it's 1, 0, 0. Again, using the traction relation with a stress at point B, for TBR, we get sigma RR in R plus sigma theta R in theta plus sigma phi R in phi equal to minus PO. Here again, n theta at B is 0, n phi at B is 0, n R at B is 1, so sigma RR at B becomes minus PO. So pay attention, these are all at B. And these are all at A. And pay attention that n in the n of R at A becomes minus 1, and n of R at B becomes 1. So far, we know that sigma RR at A becomes minus PI, and sigma RR at B becomes minus PO. Let's substitute R equal to A and B into sigma RR that we've already found. We get that sigma RR at A becomes E divided by 1 plus nu, 1 minus 2 nu, multiplied by 1 plus nu that A, minus 2 multiplied by 1 minus 2 nu B divided by A to the power of 3. And for sigma RR at B, we have the same, E divided by 1 plus nu, 1 minus 2 nu, multiplied by 1 plus nu, multiplied by A, minus 2, multiplied by 1 minus 2 nu, B divided by, this time, B to the power of 3. Okay, here we have two equations with two unknowns, A and B, that we can solve, and the result is A equal to 1 minus 2 nu multiplied by pi a to the power of 3 minus p0 b to the power of 3 divided by b to the power of 3 minus a to the power of 3 multiplied by e. And the same we can find for b, this relation based on pi, po, a, and b. Okay, the last step is calculating displacement, strain, and stresses. We found the relation for ur, u theta, and u phi. We just substitute a and b there. Also, we found the relation for epsilon rr, epsilon theta theta, and epsilon r theta, and epsilon phi phi, and the other off-diagonal elements. We just again substitute a and b there, and also for sigma rr, sigma theta theta, sigma phi phi, and off-diagonal elements, the stress tensors. So we just substitute a and b, and we find the displacement, a strain, and a stress relation everywhere as a function of r, theta, and phi. That was it. The only remaining solution strategy that we have not talked about so far is a stress formulation. In the stress formulation, we end up with an equation that looks like this. You may notice that the only unknown here is sigma, and then we find it as a function of the loading. And there is no sign of a strain and displacement here. It gives us 6 compatibility relations in terms of a stress for a body in equilibrium, which only 3 of them are independent. They ensure a single value displacement field. They are opposed to St. Venant compatibility equation, which are in terms of a strain. You remember that we had it. And they're known as Beltrami-Michel stress equations of compatibility. They comprise a system for the solution of the stress components in combination with the equilibrium equations. But the drawback is they're not specifically easy to be solved. So we don't talk about them much. In summary, we've reviewed the basic linear elasticity equations, equilibrium equations, kinematic relations with the compatibility constraints, and constitutive laws for isotropic material. These equations were combined in the displacement and stress formulations. We have learned 3 analytical solution strategies for 3D problems with simple geometries and loadings, using displacement formulation for a sphere problem, using a stress formulation, which was too complex, so we didn't do anything with it, and using semi-inverse method for a cube and a prismatic bar under simple loading.